Hello, welcome to episode 16 of the Trading Signals Coding Session series. We have just finished synchronizing the bot following signals with the bot that is emitting the signals. There are a few issues that I want to solve now. Still related to this one is that the signals at one point during the last episodes, we removed the capacity to maintain themselves in the sense that they are not being deleted even after usage. So we need some mechanism so that they don't accumulate in memory at the task level. The other thing that I would like to fix is an issue that I think it exists when the bot emitting the signals is not when the network node is not up. I think it crashes. So we will solve this one too. And if we have time, we will probably do another a little upgrade so that we can run a trading session that without signals, meaning that if you run it at the bot that is sending signal, then it will ignore the signal's definitions and it will just not send anything. And if you run it without signals at the bot that is consuming signals or designed to consume signals, it will just ignore the signal's definition and not and do whatever it can do without that. Okay, so session, I will take note here, run without signals. Okay, so let's jump into the code. Okay, here we are. Let's check our Visual Studio code. We will be using this task number one. And so the first problem is signals that never gets deleted even after use. Okay, let's go to the place where signals are being accumulated. That is here. So when a signal arrives, when a signal is received, we are storing it at this signals by candle and signals definition IDs. Okay. So today the problem is, or the way it works is that every signal is stored in this map with a key that uses the signal begin and signal end and the signal definition ID. And this is good because we are synchronizing perfectly the two bots. But once the signals are retrieved, we used to have a mechanism to delete them. But we remove it. So let me recall, why did we remove it? I think that we remove it because there were situations in which conditions that require signals were executed more than once, or formulas. And part of the explanation of why that happens is that at every candle there are two cycles, right? So this cycle concept might be one of the reasons why certain stuff are executed more than once. Probably it's not most of it, but if at least there is some, then we cannot remove the signal once retrieved, because that would mean that we would be preventing the next request to get the signals. So we were already there and we don't want that again. So my guess is that we need another mechanism, okay? So let's say that the mechanism is, hold on a second. So let's say the mechanism is that at every candle, when the loops end, and I already know that there's not going to be any, we're not going to request a certain signal anymore, I might want to delete the signals associated to that request. Okay, so maybe the way to solve this problem comes at the simulation loop, where we iterate through all the candles. Maybe. In the previous episode, we fixed a problem by moving the broadcast of a signal to the places where we can exit the loop, that is here, or where the loop is about to end, right? Here it appends record, and here we loop into the next candle. So maybe this is the right point also to remove the signal. Okay, and let's say we can do that. We will need to access this guy, peer-to-peer network interface, which is today is accessed by this guy here. But there is a way to go directly to him, to it, and it's probably as easy like this. So we are going to do this. We're going to create here I would just need to separate a little bit this code from the current existing one. Maintain maintain signals or signal storage. Okay, so we are going to send the current candle, and we are going to create a function here called maintain. Okay, so the meaning of maintain is to keep the storage with the information that we actually need. One candle that has already been fully processed means that the signals associated with that are no longer needed. Okay, so we will add this. We know we have a candle here because we are inside the loop. So we will get then event receive, signal receive, get signal. We're going to add the function maintain. Okay. Okay. So I'm going to place this one. Can be anywhere, maybe here. Function maintain candle, and that is where we are going to delete the signals belonging to this candle. Okay, as you might already figure it out, we are going to have a problem because our map, the key to our map, it, it includes the candle begin and end, but also a signal definition ID, which we don't have. And what shall we do? Well, there are several techniques we can use. Maybe we can have, for instance, an array of one it would be we can have an array of signals that we have one array of keys, of these kind of keys, from signals that have been retrieved and yet not clean it or not deleted. Okay, that would work well, except for the fact that there might be at the bot trading system, there might be signals not used. Maybe the emitting bot is emitting more signal than what this bot, the receiving one, is actually using. So if not requesting those signals, then they are not going to be deleted, and they're going to stay in memory forever. So we don't want that. Sorry, I forgot again to switch. I'm here, and this is the maintain that I was talking about. And this is the code at the trading simulation I was talking about. Okay. So here we are going to call the maintain with the candle. And here I'm going to maintain it at the same place where we are receiving the signals. Okay, so another technique would be each time we receive a signal and we store it here, we also store each key on a map per candle, right? So in a map per candle, then from that map per candle, we can retrieve all the keys from this map and delete them. Okay, so that would work even if the keys are not retrieved, but the simulation goes beyond that candle, because the simulation will be cleaning every candle there. Okay, so that's what we're going to do. Okay, so we will need another map here. These are not signals, but these are keys by candle. And the keys are the keys of this map, right? Keys by candle. Okay. Okay. So what we're going to do here is going to create candle key. Candle key is going to be this, just the key begin and end. Okay. So with this, we're going to do something similar to this, because we will need an array of stuff in there. So first we're going to retrieve from keys by candle, we're going to get the candle key. And this array, we are going to call it just keys. Okay, so if keys is undefined, then we will initialize it with an empty array. And then at keys, we are going to store the key of the other map. Okay, one key of the other map. Good. Then signals. Okay. Then in keys by candle, we are going to set, and we are going to use candle key as a key, and we are going to store there the keys array. Cool? Okay. Once we have that, what we're going to do is come here. Let's copy this again into the maintain function. So when we need to maintain this, we will receive a candle, and with the candle we are going to get the keys array. Okay, so if keys array is undefined, then we will return, because there's nothing to delete. But if not, we are going to iterate through keys okay, something like this. So We're going to get each single key at this array. And with that key, we're going to execute an hour, not at this map, but at this map. We're going to do a delete of this key, and that's it. Okay, so hopefully, if we did this call right, we will be deleting all the key, all the signals associated with the candle that we receive here. Okay, so the candle here, okay, should be used here, and this here. And this looks good to me. So if we see the simulation, we will have a maintain here, and probably we will need to maintain this here too. If we exit the loop, before the second cycle, we will also need to do a maintenance there. Yeah. Okay, so how do we test this? To test it, we will want to debug this here while we are receiving the keys, and then here when we are doing the maintenance. Okay, so let's do it. Okay, so for this test, I'm going to run this bot at Node.js. I'm going to run this Visual Studio Code, and I'm going to hook the UI with that Visual Studio Code by hitting here debug. And when both things are running, then I'm going to run this bot, and pretty fast it should stop here. Okay. So essentially this key was stored here, store one array of one item there. So what we are saying here is that we have now this candle key, only with the candle. We will retrieve this from this that is having nothing, so it's going to be undefined, and we are going to initialize it, and we are going to push this key, that is the key that we use here, into this keys array, and we are going to store it keys by candle using the candle key, okay, and the array of keys here. Okay, so it looks good to me. I'm going to let it run, but I'm not 100% sure if this is going to receive all the stuff, because all the signals have already been sent while this was in post. I don't know what happens in those cases. Maybe it received it, I don't know, but it would be interesting to figure it out. So on the other side, I can run this bot and we will see what's going on. It should stop. Okay, this is the bug that somebody should correct. Okay, so it stops here because it already processed one candle and it wants to maintain it. So it creates the candle key, it retrieves the array of keys for this candle. There should be many. These are all the signals. These are the keys of the other array. So this is not a no. So for each one, it's going to get the key. And look at this guy, has 3,823 stuff in it. Because for each candle, it has many signals, right? So 3,823. So it's going to delete one. And now it has 3,822. So after going through the array, it's going to delete it all. The only thing that we can improve here is, in my view, is that it should delete also the element at this array, because it will not need it anymore. So you can do is delete candle key, and that would effectively maintain memory very well, because after each candle passes, everything related with signals to that candle is going to disappear. Okay? Perfect. So the last test that I'm going to do with this is to, maybe I will console log here, console log the amount of elements of this. Now I don't know the property name. Maybe size. Maybe size, but I'm not sure. So that will show us in console that should show us how many signals we have accumulated in memory. Or, yeah, kind of. So the next test for this, I will stop it. I will stop this. I need to stop this, and we will run both at Node.js, and we're going to watch how the size of this map, if size is the right property. So let's run this. Let's run this. Also, at the same time, I'm going to do this test that I didn't do it so far. That is running first this bot and then the bot receiving sending the signals. So I do the two tests at the same time. So why is this not running? Okay, so we run this guy and it will be waiting for the other. Even executing is going to be waiting for the signals of the other guy. Okay, so here it comes, and you can see that they are running together, and you can see that at the map, the amount of memory used is even more reduced when they are running synchronized, because as soon as the signals are being used, they are removed from the map, right? Well, perfect. So yeah, I don't need to go to the end. For me, this is good enough. This was success. Okay, so what I'm going to do is remove this log, and also what we are going to do next is we're going to commit these changes and set maintenance of signal storage implement and test it. Okay, so problem number one solved. The next one. The next problem was about running the bot, sending the signals without having the network node running. Okay, so that is a problem because I believe that it crashes. So what I'm going to do is find the network node and just stop it. Okay, we stop it and run the bot emitting signals. Remember that the task recognizes that it needs to get connected to the network node because of this stuff here, this node, because this task is connected to a task server app, meaning that this task is going to run with a certain identity of the overall superalgo system, and it's going to have a sign-in account to sign its messages. And because that transforms this task in a network client, then it will automatically connect with a network, or at least try to do so. So when the network node is not up and running, this most likely is going to crash because we haven't handled that so far. So let's try it out. Okay, yeah. Um, well, to my surprise, it's not crashing. It's not crashing. It's just trying to get connected. It's finding several network nodes definitions, like these guys and mine, and it's trying at localhost and defining ports, and none of these network nodes are up, so it's just retrying. Okay, so yeah, that's good. uh, my I I believe that if I run the network node, is going to get automatically connected. So if one of these nodes become online, then it will recognize them. Let's try that out. Okay. Okay, and here it is. The task now is connected to my node number 1, okay? Via WebSockets, and also it made a test of an HTTP connection that was successful, okay? So if I turn the node off, or it goes offline, or the internet connection is broken, then it will try to reconnect forever there. Okay, so I didn't remember this was working, but something is not working, and probably is what happens if I try to run the bot while it is disconnected. What happens? Let's try it out. If I try to run this bot while it is disconnected, okay, an unexpected error occur. And yeah, I'm not sure it survived this one. Well, it insists in connecting to the network node, but in fact, I think that the task is pretty much dead by now. So error trying to send a message to the peer-to-peer network via its HTTP interface. Connection refused. Okay, so we will need to handle this. Run simulation. Okay, the question is, what should happen when a bot emitting signals is not connected to a network node, or the connection fails? What should happen? For sure, it shouldn't crash. It shouldn't crash, but what should happen? Maybe if the bot just continues, and the signals that needed to be sent are not sent at all, then the bot following the signal will never be able to reconnect and reprocess the stuff. That in some situation it might be acceptable. Let's say a bot that is running every minute and have a period of 3 minutes that it gets disconnected. So the optimal situation would be that when it finally get reconnected, then it sends all the signals that it couldn't send while it was disconnected. And the other bot would receive all the signals, and it will process them in order, and it would be able to continue as if nothing happened. Of course, if it was 1 hour offline without connection, without the possibility to send a signal, then the other would be replaying signals that are 1 hour old. But chances are that if the network is is there, the peer-to-peer network, the guy sending the signals will have plenty of nodes to connect to. At least that should be the case. So, okay, the important thing here is how do we make, how do we assure that signals are not going to get lost or not sent in the eventuality of lack of connection to the peer-to-peer network. That is the problem, okay? So let's go to see if we can implement the solution for that. Um, let's go to our task server one and remove the, okay, we don't have more breakpoints, only this one. Okay, so where is the place where the signals are sent? Here, trading output. Sorry, it's not here. Incoming, outgoing trading signals. Peer-to-peer network start. Where is this guy? I bet that is close to this guy. Mm, not really. So it's not part of the algorithmic trading or foundations. Most likely it's part of the network project. Maybe here. Peer-to-peer network start. Okay. This is a module provided by the network project that allows you to send an HTTP request to the network. So, and it's called network start because our network will be arranged in a certain way, as in a cyclic graph. It directed as a cyclic graph is the name, and well, it's here. Okay, so the start of the graph are the set of nodes that don't have any incoming connection. Okay, so the HTTP requests are sent to the start of the graph, and then from there they flow through the graph. Okay, so here we have a send message feature that in fact is sending the message via this guy. Yeah, because this module have an array of different network nodes that have tested an HTTP connection too. So it picks one of them, like randomly, even randomly, and send the message via any of them. So that kind of guarantees that if the network is up and you're configured to have many different outgoing connections, you might be connected to 10 different nodes, and you will be sending this signal over any of them. But it can happen that you might have your internet connection interrupted, so you cannot reach any of these nodes. So you will have to store the signal for a while until you can successfully send it. Okay. Okay, so I want to reach the place where this is really going out. And it seems that is inside of this HTTP client that it looks like is going to close some modules here. Output management. I don't need this and I don't need this. This is the HTTP network client. Okay. And this is the exact place where the HTTP post is done. Okay. Here. Okay. So from here we need to start managing the rejection or the impossibility of sending the message. Okay. That, by the way, I have one to do. I'm going to take note. I need to put this require at the root object. Okay. So let's check this out. Okay, this is a send test message. We don't care about the test message now, but about the message itself. Mhm. Okay, error trying to send message via peer-to-peer network interface. So probably this was logged here, as you can see. Because it came through here. I don't really know why 2 times. Maybe try twice. But I don't really care now. So this rejected this promise. That means that whoever was calling this guy needs to handle the rejection. And of course, it's not doing it. So what we are going to do here is we are going to create a response message based on the interpretation or of this call. So this is the way I'm going to do it. To this await, I'm going to add a then close function message sent, and then I'm going to create a catch message not sent. Okay. So here I'm going to create a function message sent, in which mhm, I'm thinking that maybe I need to return a promise from this too. This is called from where? From network interface? No, from outgoing, from here. So this outgoing trading signals is the one who is going to store all the signals that have not been delivered so far. Okay, because this guy doesn't know about signals, it knows about messages. The same that this guy, he doesn't know about signals but messages. Um, so when we receive a response here, then okay, there's also a tutu here that we need to check that the network node actually accepted the message and not just crash or did something bad or have something bad happen to it. Uh, so we'll need to take care of this too. Yeah. Okay, so my guess is that the right thing to do is this. I'm going to copy this or copy everything into here and return a promise. Okay, just return a promise. And I'm going to replace this by the previous code. And here I will have two functions. I can probably resolve or reject here. But this is like more explicit, more easy to understand. Here resolve, and here we reject. Good. The reject must be like this. Okay. Then I will copy this and take it down here. So here, this await, this just send the message and he doesn't care about anything. Good. So now it's going to care in this way. But instead of resolving or rejecting here, we are going to do something else. Okay. So now here is the place where we need to implement the mechanism to store all the signals that could not be delivered. Okay, this is what we're going to say. Store in memory all the signals that could not be delivered. Okay. And if the message was actually sent, then probably we are probably good. Okay, so how are we going to store all the signals that could not be delivered? Well, easy. We will create here at the object level an array of signals that could not be delivered. I usually define this here and we initialize it here. And we destroy it here. Now how things work over here. Hmm. So this signal message is an object at this point in time, which is okay. Yeah. It is okay, it doesn't matter. So message not sent means that we're going to add one more item to this array, specifically this one. Okay. So yeah, each message that could not be delivered will be stored here. And once that happens, this will start accumulating signal messages. Okay. Good thing that they are going to be in order because their push is pushing at the end of the array, adding one more item there. Okay, so when we send a message, okay, probably here what we need to do is to iterate. We need a way to iterate until we finish sending all this stuff. But I see a few problems there. Um, okay, so which is the problem we need to solve? Every time a signal is going out, we cannot send that message because if there are other that are pending to be sent, they have priority. It's not that it's very much important because the bots following the signals are going to do it candle by candle, And if I send, but yes, it's kind of important in the send. What if I send the signal that allows the bot to go to the next candle without having sent the signals of the formulas of that candle? I will create a mess. So that means that the order is important. The order is important. Okay, so we cannot send the next signal until we don't send all the signals accumulated in this queue. So one would think, okay, let's iterate this stuff and send all the messages. But the problem is that while we are iterating, we might be adding more stuff to the same array. Okay? And we don't want to do that while we are iterating, because that would create like a kind of a mess. So let's see if we can put this clear. What we are going to do is we are going to iterate the existing array e equals 0. Okay, one possibility is that we add to the array the item that we need to send, and if it is empty, it doesn't matter, because we are going to iterate through all of them. Trying to send all of them. Okay? So here, let's send next signal equals each item of the array, and for each one we are going to do this, and instead of sending signal message, we will be sending next signal. Okay, that seems to look good, because here there is an await. It's not going to continue the loop until we don't have a clear response if we could do it or not. At the same time, we will need of not the signals array right here that is going to be accumulating the messages that could not be delivered during the execution of this loop. And finally, we are going to override this guy with the contents of this guy. Okay? So a few comments here to clarify what we are trying to do, and it's like this: iterate through all the, it cannot be called signal could not be delivered, because it's also the signal that, so this better name would be signals to be deliver it. That would be a better name. Signals to be delivered. Signals to be delivered, including the one that is being sent right now. Okay, so we are coming here. We have the message to send is this guy. So we create this array, an empty array with the ones that could not be delivered. And we add the signal to be delivered, this guy. So this is going to execute at least once. And it's going to take the next signal. It's going to take the next signal, number 0, index 0. It's going to send it. If it succeeds, then pretty much nothing happens. But the loop can continue. And because there is no other signal, it will replace the signals to be delivered that had one item with one that have 0 item, and it will go away. So the next execution comes here, adds this to the array, and sends the signal, but it fails. So it comes here and is added to the not delivered signals, and then it replaces this array that is exactly the same as this one, but now this array is going to be stored at the outgoing trading signals object. And pretty much this mechanism was supposed to work, except for one fact, that there is no guarantee that this object, this module, is unique, because it's being instantiated at many different places. Okay, so that means that at some places it's going to store some signals, and at some other places it's going to store some other signals, because the same module is instantiated more than once. Is instantiated wherever is needed. So that means that this mechanism cannot be here, but we will have to move it one layer up here. That is a place which is instantiated only once. Okay? So peer-to-peer network start. So that means that what we did here is not going to stand here. We need to move the other stuff here. Well, okay, let's do it. So we made some definitions here. Of course, at the other level, it's not going to be called signals, but messages. We will do a refactoring afterwards. So here, signals to be delivered. The initialize will create an empty array. And the finalize will destroy the reference to this object. Cool. So then we will copy this stuff into this node, peer-to-peer network start. So at the send message, give some space, and it seems that we are going to do this. Okay, how do we put these two things together? First, we are going to pick which node we are going to send the signals through, but not then I have a question. Are we going to send all the batch of signals through the same node or through different nodes? If we do it through different nodes, we cannot guarantee the order of the signals. No, we cannot guarantee. But if we do it through the same node, we might have the problem that we are sending too much stuff too quickly. But I will bet that that is better than sending it in different order. So what I'm going to do is that the part of the code that selects a network node, I'm going to put it first. So the whole loop runs towards the same peer of the network. Okay. So instead of calling this guy here, this should call this guy. Okay. So we know that message sent doesn't do nothing, and message not sent. I'll do this stuff. So here there is no promise anymore. There's no promise anymore. Okay, so here it says next signal, and it looks like it might work. So this message is what it used to be, the signal message. So it enters here, then it becomes next signal that comes here. And this is signal message is now message coming through this parameter. Okay, it looks good. So next signal would be next message. Okay, and signals to be delivered is going to become messages to be delivered, and not delivered signals will become not delivered messages. Not delivered messages. Okay, so next thing to do is to undo the changes we did here, because this should continue as it was before. So the outgoing signals is going to work in the same way. Once it have the signal here, it will await for this guy sending the message. We're going to debug this. This is going to come into here, and it's going to try to send the message, and it's going to await this, but it's going to handle the rejections. So if there is a rejection, it's going to add this here and continue with the next loop, and so on and so forth. Okay, so I think we are ready to test the mechanism. There is some probability that it's going to work. Okay, and the way to test it is we're going to run this. We're going to connect the sending signals bot here via debug, and the network node is going to be turned off. Okay, so that means that this guy is going to be trying to connect to the node unsuccessfully all the time. And we're going to stop at the first try of sending a signal, and we're going to monitor the whole circuit. So here we go. Sending the signal. And here we are. The first signal is this one. We enter F11. Yes, we are here. We got the signal. Yes. So we pick a peer. The peer is undefined. So this is another type of situation where we cannot pick any peer because there are no peers. So the peer is undefined. It's not that there is a fail inside the network node, but the problem here is that there is no network node at all. So this is not going to work at a very fundamental level. So I should check here if peer undefined, then what are we going to do? I guess that we are going to add the message before. Adding the message to the queue to be delivered. That's one of the first things to do. If the peer is undefined, then we just return because we are remembering the message and there's nothing else we can do. Okay, so this other situation is when there is a peer but something fails. Okay, but something actually fails. I wonder what is going to happen here. Yeah, cannot read property of undefined. Yes, it's reasonable. Okay. So next test we're going to do is we're going to have the network node running. But we are going to force the network node or what we are going to do is the next test is we're going to have the network node running, let it come through here up to here, then we are going to turn it off. Okay, so it thinks that it have a peer, but then it doesn't have it. That's the next test. So let's run this one. Okay, turn it off, run it again. Turn the network node on. And let's connect the UI to the Visual Studio Code task. Okay. Okay, it's connected to network node 1, but oh my god, this is not resetting automatically. Okay. Okay, so there is a peer and it's going to move forward, but we're going to turn off the network node. So the peer will not exist, in fact, but this believe that it does. So here we get the next message. We have not delivering 0 and this in 1. Okay, so we will put breakpoints everywhere because I want to certify that this is going through the path that I believe it's going to go. Send message. So it's going to return a promise, but it's going to enter into here because the other guy is going to be awaiting. Yes. This is going to work. And it's going to make the post. And it's going to catch it here. Okay, error trying to send message to be whatever. So the reject is going to send us back to the reject here. Yes. So we're going to add this to the not deliver. And then this is going to come here because there are no more message to be delivered. But we will have here one element, here one element, but it's going to be overwritten by this one. And this is going to continue, and the next one is going to come. Of course, now I don't know if this is going to realize that the peer is not connected anymore or when. We will check it because this will try to come again here at the next signal. Here it comes. So peers, yes, it still believes it's connected. I will take a note. Handle HTTP peers disconnections. Because at some point, I don't know if there is a handling of this. Somehow it gets to understand that it's not connected anymore. This make and a way to this make this probably once, I don't know, I have to check that. That's a matter of another episode. But here this guy will try to come again. So it will add this to the message to be delivered. So now there are going to be two messages. The peer is not undefined. So now it's going to iterate through two different messages. Then it will try to send them. It will fail and it will come here. And the not delivered messages, we're going to add one. And it will continue trying to deliver the second one, which is going to fail, and it's going to come here and it's going to add it to the not delivered. So in message to the deliver, there are two, and here are two. Remember that there's no guarantee that not all messages are not going to be delivered. So maybe there are 10 to be delivered and 5 could be delivered and the other 5 couldn't be delivered for whatever reason. So that's why we are reassigning this into here. Okay. But as far as I can see, the mechanism is working, because if we turn, for example, let's turn the network node on, and run this a little bit more, then we have the third signal. It's going to come here. So we have 3 to be delivered. Then one comes. So this will try to deliver it, and it's going to be good. So in this case, went good, so it goes to the next one, and it's going to deliver it too. But the third one, we are going to turn off the network node, and it's going to fail. So the third one goes with a reject. So it will add 1 to this array, and this array that have 3 messages now will have 1, because 2 signals could be delivered and they were delivered in the right order. So here we go again, and in the next cycle we will have 2 messages to be delivered. Okay. So okay, very good. So we implemented here a mechanism by which we are going to remember the messages that are not being delivered and automatically try to deliver when another signals come. These obviously have a limitation that it might happen that the last message is not delivered and there are no more signals left to be sent. So probably there is no more retries, and there might be pending signals that cannot be delivered. And not only the last message, but let's say the last 100 messages. Okay. So to polish this, we will need some mechanism that automates the retries. So I will take note of this. Automate the retries. So that it does not depend on the on new signals. Okay, that's one problem we need to solve. Um, the other one that I took note is the HTTP disconnections when the peers are when the node is get disconnected. It seems that there is no discovery mode to recalibrate which nodes are available. So we need to program that too. What else? We have some stuff to do. When the peer-to-peer node is sending a response, I will take note of that. Peer-to-peer node sending a not okay response. Okay, we are assuming that the response is enough to consider the signal to have been delivered, but that's not reality. Maybe the network node is telling us something, like bad signature or something, and we cannot consider that uh, an okay response. Okay, so I have taken note at least of 3 stuff that still is pending, and we can cover tomorrow in another episode where we are going deeper into the problems of sending signals over a peer-to-peer network. Plus, I have another one here, that is that access dependency needs to be properly defined at the root object. Okay, so good. We cover a lot in this episode, and hope you like it and you find it interesting. And if you did like it, come back again at the next episode where we will be solving the other problems that we have in our queue. Okay, so thanks for watching this one and see you next time.